How does MyScale compare to some of the dedicated vector databases?
So if you have some familiarity with SQL, then you basically need no learning curve with MyScale.
Do you think that basically like all databases in some fashion need to be open source at some point?
Certainly not all. I think most, I would say, for like more independent companies, I think open source is it's often a good move. So you can get more feedback, and you can get more use case, right? So and you can get more trust, like to between you and the users, more technology transparency. But frankly, you also need to think carefully about like how to commercialize your product.
In terms of a vector, you mentioned at the beginning there that essentially a vector can be the representation of an object in sort of compute space. So can you just explain a little bit about how that works? Like if I have an image, how do I essentially turn an image into a vector that then represents that image? Hey everyone, Sean here from Software Huddle. Welcome back to an episode where we're talking vectors, vector databases, and AI with Linpeng Tang, CTO and co-founder of MyScale. MyScale is a super interesting technology. They're combining the best of OLAP databases with vector search. The project started back in 2019 where they forked ClickHouse and then adapted it to support vector storage, indexing, and search. The really unique and cool thing is you get the familiarity and usability of SQL with the power of being able to compare the similarity between unstructured data. I think this has really fascinating use cases for analytics, well beyond what we're seeing with other vector database technology that's mostly restricted to building RAG models for LLMs. Also, because it's built on ClickHouse, MyScale is massively scalable, hence the name, which is an area that many of the dedicated vector databases actually struggle with. We cover a lot about how vector databases work, why they decided to build off of ClickHouse, and how they plan to open source the database. Before I get you over the interview, Alex and I will be in Miami in April at the Shift Developer Conference doing interviews. If you're in the area, you should come on by, see some great talks, say hi to us. You can learn more about the conference at shift.infobip.com/US. Okay, let's kick you over to my interview with Linpeng. Linpeng, welcome to Software Huddle.
Hi, Sean. Nice to meet you. Yeah.
Thanks for jumping on doing this. So you're the CTO and co-founder of MyScale, a SQL vector database. So can you give me the backstory of MyScale? Like, how did it start? Where are you guys today?
Yeah, actually, ever since I finished my PhD in Princeton Computer Science, I have been doing things related to machine learning, deep learning, and big data. And actually, we started this idea, I think, in 2019 or 2020, something like that. And we have been doing this for the past 4 or 5 years. But the SaaS version just launched last year. And our MyScale currently is headquartered in Singapore, but we have a distributed team across Asia, Africa, and North America. Yeah.
Yeah, it seems like there's a couple different like companies in the vector database space that are like had their headquarters in Asia. Do you think like is there something that kind of led to like some of these companies kind of like leading the forefront of the vector database technology coming out of Asia, or is it just a coincidence?
I think currently it's a hot area, and we have different companies like Pinecone is primarily in US, right? And Vivid and Qurent, they are in Europe. So and I think it's an important area. So you see companies popping up all around, right?
Yeah, I guess there's a complete geographical coverage by everybody, but. So you went directly from completing your PhD to starting MyScale, is that right?
We did something related to machine learning, deep learning before, but it's also related to vectors. And this product launched 2019, 2020, something like that. Yeah, yeah. But I have been doing startups since my graduate school. Yeah.
Okay. And then how was that transition kind of like moving from more like, working on academic projects? Like how did you balance, I guess, like sort of working on an academic project, but also like starting a company and the transition to doing the company full time?
Yeah, I think it's just a comparison between working, say, in big corporates and doing your own startup, right? I was actually interning at Facebook for several years, actually doing internship and contracts. And, it's a hyperscaler, right? Because what you do, even it's a small amount, you can affect, say, 1 billion or 2 billion people. So actually you can make a difference. But in startup, like your the scalar is much smaller, right? You can only affect a much smaller percentage of people, but you can actually make a huge difference. You can make the product 10 times better, or even 100 times better. So they are all possible. So I think it's just different pros and cons, and I think it's more interesting to work on like 10x and 100x problems, and hopefully to affect more people. Yeah.
Yeah, absolutely. I think I'm there with you. Like I think the impact of working for like one of the big FANG companies or one of the big companies is that like a product you work on or a feature you work on could legitimately be used by like a billion people, which is pretty cool. But it's a lot harder to make these huge leaps in terms of like a 100x improvement and so forth because the product's been around for 20 years. A lot of those like easy wins or improvements have already been made. And then it's also harder, I think, to make like company level impact when you're in 100,000 person organization versus.
I totally feel you there. Yeah.
Yeah, exactly. This is your baby. You can do whatever you want. So, but that also means there's also a lot of pressure on you.
Yeah, of course, but it's different choices, right?
Yeah, exactly. So let's get back to vector databases. So before we get into the specifics of MyScale, I just, what is sort of the value of a vector database? Why are they so popular in use in combination with LLMs? Just so that we can kind of set context for people who are maybe less familiar with this area.
So even before large language model, I think vector databases are pretty important in machine learning because a vector is a universal representation for like images, like audio and also text. So they were used in like similarity search and also like recommendation and other systems. And I have been working on those areas before the LM era. But since LM, because it's such a important and universal technology, and actually vector database basically serve as the external memory for the large language models, because large language models, they have several issues, although they are very useful. First, that the knowledge is static, right? So once you train the model, like they don't update until like you get a newer version, which might be half a year or 1 year from the initial version, right? But you cannot get the latest knowledge. And second, there are so many vertical areas of knowledge. Say you are interested like in say finance, or like a like a knowledge base within a enterprise, like those the large language cannot access those knowledge. So basically, vector database serve as a way to like bind the large language model with these up-to-date and like specific and vertical area knowledge. So you ultimately you get a more useful system. So that's a common pattern, and that's why it's so universally useful. Yeah.
In terms of a vector, you mentioned at the beginning there that essentially a vector can be the representation of an object in sort of compute space. So can you just explain a little bit about how that works? Like if I have an image, how do I essentially turn an image into a vector that then represents that image?
Mm-hmm. Basically, you have different models for before the transformers get popular. You are actually using like convnets or ResNets, like with the convolution, mainly architecture, and you take the bytes of the 2D image and then transform it to a several convolutions and then to a 1D vector and something like that. And nowadays, like transformer, the architecture, because it can take care of both the global like correlation and also like look at like non-local correlations compared to the convnets. So they are more powerful, and they're basically taking over both the text, the images, the videos. So nowadays, people are largely using transformer architecture to transform the different modalities of data into vectors, right? And then semantically similar like objects will be also nearby in the high dimensional vector space, and also they are often tuned for different purposes. For example, when you are doing like question and answering, you not only like cluster like similar paragraphs into nearby vectors, but you also train it so that the question the vector representation of the question is very close to the context for answering the question. So that's why it's so powerful than a traditional, say, keyword-based searches like BM25 and such, because they can basically consider the semantic relationships between the question and the answer. Yeah.
Yeah. So with the vector database, in the context of LLMs, I'm using it as kind of like this external memory where I might have domain specific information, or I might have information that's more sort of like real time, and the foundation model doesn't necessarily need to be as up to date. It's kind of like I have, things going on in my mind, but then if I need additional information, I can go and like Google additional information. It's like serves as my external memory essentially, right? So sort of same idea in terms of an LLM. But then in terms of the use of the vector database, essentially, we're taking a bunch of objects, we're transforming them into vectors, into this high dimensional space. And then the job of the vector database is to kind of like organize those vectors into a way that we can figure out, okay, this object's actually similar to this object, or this, for this question, these are the potential answers. Is that right?
Yes. So vector-based basically provides you a way to manage and query vectors and other metadata, right? So database is such a technology that dates like 70 years ago, right? And they have been moving around structured data, then NoSQL data, then big data, and then SQL again, and then now vectors. Yeah, so you see these traditional technologies, but the basic thing is to manage, query, search, right? So yeah.
Yeah, I mean, like the relational database, like you said, goes back to like, I think the first commercial relational database is from like the late 1970s, and then SQL came, shortly after that. So it's been around, it's been with us for a long time. And then it's really only been sort of the last decade or so that we figured out ways of starting to sort of unlock like unstructured data so that we can actually use it. And it feels like the vector database is kind of like the next natural evolution of that, of being able to take things like videos and images and actually make them useful in a way that we can search, index them, and compare them.
Yes, of course. So it's very, very, very exciting area where we're seeing many potentials in this area.
Yeah, awesome. Yeah, and I think that's probably why this is such a like interesting area, and we have a lot of like players that are sort of starting to come to the forefront of the vector database space. So I want to start to talk a little bit about the specifics of MyScale. So ClickHouse is this like super fast open source column oriented DBMS, and actually recently I took part in this 1 billion rows challenge back in January, where the idea was to take a file that contains 1 billion rows about data from temperature observations. And the goal was to figure out like the min, the max, and the average temperatures by location, print that out in alphabetical order, and do that as fast as possible. And the original contest was for Java programmers. So they wanted to see like how fast could you do this using just pure Java, the latest things in Java. But a bunch of people started to do this with other types of technologies. Like I did it with Snowflake, but I saw one person actually do it with ClickHouse. And without any kind of like optimizations, they got super impressive results just running it on their local machine, which is pretty cool. But I guess so essentially MyScale is a fork of ClickHouse. That's how it started. Like, why did it make sense to essentially take this like column-oriented, like super fast database that's for analytical store and sort of turn that into a vector database?
Yeah. So there are different ways of doing a vector database. So you see all these specialized vector databases such as Pinecone, V8, QGent, Milvus, right? So but when we started, we want actually not only want to do a vector database, we want to do a database that's designed for AI, and then back then there was not even LLM. We want to do it for all AI related data. So that would include like structured data, like JSON data, text, time series, geolocation, and others, right? So they will naturally include all the modalities because they're so widely used, right? And you see they are also useful in many situations. So we didn't want to reinvent the wheel. So we want to also take existing technology and transform into to something greater, right? So we want to do it based on based on a SQL database, because SQL, I think that mathematically speaking, the SQL is very beautiful. It's like a relational algebra. So we want to do that. And then there is a question of choosing whether a row storage database like PostgreSQL and MySQL, or a column storage like ClickHouse was a natural choice for that, because it's a very fast open source Apache licensed column base. And then when we started looking at vectors, we realized that actually you need a lot of fast scanning in order to combine structured data and vector data well. For example, often you want to scan on the structured data first, very fast, and then fill out and then find out a subset, and then run vector search on the subset of the data. So you see this pattern again and again. So in order you want to do a local search, or you want to remove the non-related data and something else. So actually column data is very bad at that. Row-based database is very bad at that, because each time you need to read the entire row, right? So, but for ClickHouse, the column it's compressed, and you have all the skipping depths, and also you have the SIMD execution. So it's very fast, and you can store all the big data and query it with SQL. So it's very nice. So that's why we decided to implement based on ClickHouse. And also, but it has some disadvantages, because you cannot process the transactions well, because if you need to have a lot of small write transactions, and ClickHouse is very bad. But we find actually for AI workloads, for most of the AI workloads, you don't need that. So you can actually work around that. But we still need to optimize, say, for point reads and such and such. So we actually need to modify ClickHouse a bit to suit the AI workloads better. So that's the story.
Yeah, in terms of the transaction speed, so there you're talking about transactions in terms of writes to the database. Is that correct?
Yeah. So a row-based database is very fast and write transactions. Yeah.
Yeah, but that's not the most common use case, I would think, in terms of a vector database is you need to be able to read and compare, basically, find out that this object is similar to this other object as quickly as possible. And the writes probably happen in batch if we're talking about something like, retrieval augmented generation or RAG.
Yeah. And they don't modify the data often, right? They just do writing batches. That's most often workloads. Yeah.
Yeah. So that changes. That's why we're the row level wouldn't necessarily make sense. So the ClickHouse, my understanding is it supports some level of vector search natively. So I guess what did that already exist when you started MyScale?
When we started, it didn't exist yet. So, and now I think it has the experimental support for vector search, but I don't think it's very mature yet. And we are actually doing even better than the mature vector database, because we did so many optimizations on both the vector algorithms and also modify the SQL execution engine and the storage engine. So we are actually open source the product very soon, I think by late March. So we'll see. Yeah, so you'll see the code. And so actually we forked from ClickHouse, but the whole project, I think we are oriented as just the AI workload. So that's our differentiation with ClickHouse. We are mostly interested in the vector and structured data related search and the analytics. And for the OLAP features, we actually contribute a lot of the features to the ClickHouse open community. So I think there are also because ClickHouse is such a great product, so I think there are also other folks like us. Yeah.
What was involved with actually transforming ClickHouse into a something that could support the vectors?
So first of all, you need the vector algorithms. I think that's suitable for the OLAP system. I think for example, the graph-based vector algorithms are very popular, but they actually build very slowly, and they also take a lot of resources. So I think that's not very good. So actually, we only use the graph structure in our algorithm very, very, very consciously. We would combine the tree structure, which actually builds faster and does better at filter search, and combine it with the graph structure and design our own vector algorithm. And also we fuse the algorithm with the SQL execution engine and the storage engine, you also need many modifications like that. So, for example, how do you combine the structured data and vector in a single query, and the query can be very complex. And sometimes you need to do the structured data filter first. Sometimes you need to do the vector search first, right? How do you do that? And also the storage engine is also very complex because the structured data, you basically ClickHouse does something like a merge tree, but structured data, they merge very fast, right? You can easily merge two data bars. But for vectors, when you do the merge, you also need to rebuild the vector index at least in some time, right? So, but vector index rebuilding is very slow and takes a lot of resources. So how do you handle that? So we need many modifications on both the execution and the storage. And also, in addition from vectors, we are also adding many advanced search technologies, like we are adding inverted index, like for keyword search and other stuff. So gradually you deviate from the original OLAP thesis and adding all these features. Yeah.
So what's a situation where I want to join information from like the vector side of my database with the non-vectorized data store that's, maybe traditionally organized into tables, rows, and columns?
Yeah. So there are many use cases. So for example, you want to search for a restaurant, right? Say near your current location, like say within 10 miles or something like that. Then basically the geolocation is more like a structured data, right? We also seeing people want to search against very complex documents. And they in financial documents, then they sometimes want to filter on the company name, which is like a regex string filter, and then do the vector search. And also, in many cases, vector search is quite fuzzy, so you want to, in many ways, you want to narrow your search in order to get accurate results, and you see all these combinations. And in real case, we also find the SQL data model we think is quite useful because so recently we have been collaborating with our clients on these academic projects where they actually store and query hundreds of millions of papers. You actually come with 20 tables for this project, and they store it in MyScale, and sometimes you store some of the attributes with vectors and store others in other tables and do the joins, you do the updates. So actually, you see in these real world examples, actually you need the SQL semantics, right? Just vectors is not enough, and we see this again and again, right? So, and we are seeing this is a norm in the future.
Right. Like if I wanted, like in the e-commerce sense, I could do something like I want to, I don't know, show me navy blue T-shirts that are within, I don't know, 3 miles from my home and are of this brand. So then, essentially 3 miles from my home is going to be like a box based on like the geolocation. So I can do that using sort of traditional database lookup. I can look up the brand, but then navy blue, I might want to do some sort of like vector-based similarity search, because if I asked a person that and they were like really knew the where shirts are sold and were like a retail guru, like they might recognize like, okay, well, there's not a navy blue shirt at this place that's only a walking distance from your home, but they have a baby blue shirt or something like that, and they would give you that option essentially. But traditional search can't really perform that kind of operation very well.
Yeah. So I think like Elasticsearch, they are also adding this functionality, but I don't think they perform well with all these complex filters and analytics. And what I think is even more useful to do not only search but also do the analytics, right? So you want to analyze different styles that people which styles they prefer in different age groups or different locations, right? You can do all these analytics, and how do you do that with just a simple vector search, right?
So can you walk me through what's actually happening when I at the query engine level and the indexing level when I write a query like that, where I want to essentially do a join across or I'm essentially doing a lookup on a particular column data, but I'm also essentially doing a similarity search across the vector store as well.
Yeah. So there are different execution paths. So for example, PG Vector, they do this post filtering. So they do the vector search first. And then after you get the candidates, they basically filter on the conditions. But if the condition like percentage of matching rows is small, then you might fill out almost all the results, or you might get very inaccurate results. So that's why we benchmark PG Vector and see the filter accuracy is very low. And the other way that we do in ClickHouse is actually mostly pre-filtering. Pre-filtering that you condition on the structured data first. You find the rows that matching this condition, the 1% of the rows matches, and then within that 1%, then you basically compute a big map. But sometimes it can be done very efficiently, especially you organize the data like according to this label. You have all these skip index and such. You can do it very efficiently, and then you do the vector search within that small range, and then your vector search algorithm need to be very friendly, very fast, and very accurate with these almost arbitrary filtering conditions, and then you return the results. So that's how we usually do it. But because SQL is very flexible, we also provide the option if you want to do the post filtering. Sometimes that's useful if the conditioning is very complex and costly. So you see this flexibility with SQL and vector together. Yeah.
Okay, so basically you're reducing the search space in sort of the traditional case. You're first reducing the search space by matching against sort of the traditional database like columns and indices, and then let's say we get like 100 potential matches there. Then you're taking essentially the vector input and comparing it against that reduced search space of the 100 and figuring out what is the most likely candidates, and then you're going to have some level of similarity between the input value for the vector search and all the potential results. So how do you know where to cut off essentially the value of similarity that is high enough to actually be valuable to the search?
That's a good question. So currently we just provide the top case search. So after narrowing down the candidates, say 1%, like based on the metadata filtering, then we do search and we just return you, say, the top 10 or top 100, and then you can decide like whether those are useful or not based on the distance or something like that. But also, I think sometimes it's also useful to provide, say, the range query. Say you want to return all the results with similarity larger than, say, 0.7. Then even it's 1,000 or 10,000 results, you want to return all of that. So I think that's also a interesting feature. Yeah, but we haven't actually done that in MyScale yet.
So the idea there would be I would essentially, as part of my query conditions, I could say check the similarity between like the input vector and the results and make sure that it's above a certain value or certain threshold that makes sense for the query operation I'm running.
Yeah. Usually, I think most of the use case is just a top case search. You just return the top K, but sometimes you want to return all the results larger than a threshold. You can also make it that with top K because you find say 100 is not enough, then you can increase it to 200 or 400 or 1,000.
Do you think, given that the sort of interface into MyScale is SQL, that there's certain advantages that make it more accessible to, like, say, like a traditional data analyst that is used to working in SQL, where if they were working with a different type of vector database, then they kind of need to learn a new like way of actually querying those vector databases. That's like maybe it doesn't feel natural. Like if you look at even in the warehousing space, Bigtable originally BigQuery didn't actually support SQL. It supported like a domain specific language that Google had come up with, and that was fine internally when it was an internal project, but then when they released it to the public, it was kind of it lost traction essentially because analysts were like, well, I don't want to learn a new like domain specific language. I've been working in SQL for a decade, and then that essentially helped I think companies like Snowflake and so forth like really corner that market. So there's I would think some value essentially of like enabling this kind of search to people who are who are been working in SQL forever that maybe is not available to them with some of the other vector database technologies?
So I think the data analysis, I think SQL is a de facto programming language. So we have like customers in financial that they prefer SQL a lot, and also I think the other customer in the news agency, I think it's New York Times. They also analyze the government data. They also want to use SQL, and also because SQL is so widely used, that the large language models know SQL very well, so they can even help you like translate from text to SQL, right? So even people who doesn't want to write a long SQL, complex SQL queries, they can also do that, right? So and for like complex use case, yeah, SQL is very powerful. Like even for Elasticsearch, right? It's just started from search, and with their own domestic language, they also gradually added SQL-like interface to their system. So I think SQL is pretty important, and it's basically you see SQL and then NoSQL and then new SQL. So SQL is coming back and taking, I think, a very large portion of the data management system space.
Yeah, I mean, even NoSQL, like the sort of traditional NoSQL databases support SQL now. So the NoSQL is not really like a valid name for, MongoDB and so forth anymore because it actually supports SQL. It's like every time someone tries to kill SQL and bring something else in, like it ends up being like pulled back in because it's too widely used and it's hard to sort of like shift away from the existing momentum and all the users that have been working in it forever.
Yeah. I think that's very beautiful. It's something designed like 50 years ago and still widely used, and people just cannot get it away, right? but also we are seeing that SQL is also incorporating NoSQL because you see like this native support of JSON in many databases, right? And also you are seeing some sort of like a mix of between row and column storage, right? So we are seeing this like a fusion of different technologies, and we are also doing that. We are basically fusing SQL with vectors, right? So
yeah, like Snowflake now is launching Unistore, which brings essentially the transactional database and the analytical database together in some fashion. So in terms of MyScale, like how does data modeling work? Am I creating a table that essentially contains traditional structured data as well as vectors?
Yeah. So basically you have different columns, like you can have like traditional structured data columns, and you can vector columns, and you can even have more than one vector column. You can have 2 or 3, and then you can decide you have 3 vector columns, and you can decide that you want to build like indexes on 2 of them, and that's fine. And then as long as you build the index, then you can do very efficient like approximate nearest neighbor search. Otherwise, you can only do brute force search. You scan the whole column, which is not very efficient. So you can see you can blend all these data modalities and different operations like with SQL.
What kind of data can I vectorize?
I think now almost all like unstructured or complex data can be vectorized, like images, videos, text, sound, time series. Almost all. Yeah, I think. Yeah. And basically you see this convergence of the algorithm because they are now all using like a transformer architecture, and people are also talking about the ultimate algorithm. Like I don't think transformer is the ultimate algorithm. I think it needs some improvement, but it's a good structure, and also you need the algorithm to like adapt with hardware well. You see like GPUs are getting faster and faster, so basically you need to adapt the algorithm to the GPU platform. So you see like this very beautiful reason of like software, algorithm, and hardware, and then like coping with the unstructured data. Yeah, all coming together.
And we talked a little bit about like essentially determine the similarity between vectors so that you can figure out like, okay, well, this is these are the potential answers, or this object is similar to this other object. But in terms of determining similarity, there's lots of different ways to essentially do that in vector space. So like, what is the metric in MyScale in terms of determining that 2 vectorized objects are actually similar?
Yeah. So I think the most common used metrics for like floating based vectors, they are the like the L2 distance, and the IP distance in the product, and also the cosine similarity. So basically compare distance after normalizing the vectors. That's for floating vectors. And also for the binary vectors, I think you can just compare the L1 distance or the Jacquard distance. So that's I think those are the most useful. And you have other metrics. I cannot enumerate them all, but those are the ones we also supporting in MyScale. Yeah.
What is L1 and L2 distance?
L1 is just like the other name for L1 is called the Manhattan distance. So think about the points in a grid, and then you cannot travel in diagonal, right? You can just come up and then come in vertical and horizontal. So that's the L1. And for L2, you can travel like from one point to other, like in a straightforward fashion, right? So that's L1 and L2. You can think about that.
Okay, so it's like, are you traversing a city grid versus essentially I can go as the crow flies and go direct from point to point?
Yes.
And then is this a choice as a user of MyScale that I'm making in terms of which similarity metric I'm using, or is this something that MyScale figures out for me, or essentially what are the options there?
Actually, for those distances, it usually depends on the model that you are using. I think nowadays, many for the semantic retrieval, most of the models are using the cosine similarity, right? So and sometimes they are returning the normalized vectors. So the square of the elements of vectors sum up to ones, and then in this case, the cosine similarity is actually the same as the L2 distance in this way. And for the
dot product,
and also to the dot product, they are all the same if you are using normalized vectors. So that simplifies things a lot. So so I don't think this is an issue. So but you need to figure right. I think the other simplification we made that we made the algorithm parameter very simple. So if you use the vector algorithms like the IVF or HNSW, you have all these parameters that you cannot figure out why. But we actually made our in-house algorithm very simple. So you actually don't need to configure anything when you build the index. And we provide just one single knob. We call it alpha. Like alpha is from 1 to 4. And if you choose 4, then you are very accurate, but a bit slower. And if you choose 1, and it's very fast, but you lose a bit of accuracy, and you can do trade-off in between. So I think that's actually one of the pain points of many of the vector search libraries and also the database. So you really need to make because users there's so many complexities behind these different algorithms, and you actually want to just provide very simple tuning knobs for the users.
Yeah, I mean, it's like there was a time with even regular relational databases where you needed a DBA that was doing a lot of performance tuning and so forth. But now with most databases and managed services, unless you're reaching a certain you're really pushing the limits of the database, you can kind of use a lot of the out of the box settings, and for most people that's good enough until they reach a certain level. And the ideal, of course, in the world of vector databases, although it's much newer, would be that a lot of those things are offloaded to me because I'm not an expert in how to tune these things. I just want to get my RAG model working or something like that.
Yeah. So that's why we simplify most of the things for our users.
Yeah. And then I want to talk about the indexing. So, in a conventional database, you're adding an index to a column so I can avoid a full table scan when I'm doing a lookup or partial match. With vectors, what's the sort of inner workings of creating a vector index?
Yeah, it's somewhat very similar to the traditional structured data indexing. Yeah, because you basically you basically do some sketches and clusterings of the vectors. So you have different clusterings. You can compute you can compute discrete clusters. Say you have 1 million data, then you cluster the data into say 1,000 clusters. And then when you have a query, you have the locality, right? You don't need to search against all the clusters. Maybe just you search 10% or 5% of the nearest clusters. Then you get a speed up of 10x or 20x. right? And for the graph structure, you are basically doing greedy descent. So you start from one point, from a query point, and then you immerse through the neighbors, and then you basically find the point that nearest to your query, right? So that's a graph structure. So you basically you can see that you are computing the index according to the locality of the vectors to accelerate your computation. And you can also do compression, right? You can do dot product quantization or other technologies. So you don't need to do computation on the full precision of the floating vectors, but only do approximate computation on a sketch of the original data. So that's also much faster. So you can employ the combination of these different technologies, and then you can get to the acceleration of say 100x or even like 1,000 times faster, right, or more efficient. So that's why if you're dealing with vector data or large quantity vector data, you need the help of vector database and vector indexing.
And then, so for the graph approach, like essentially, I'm building a graph where essentially, one node is going to be connected to other nodes that are similar to it, and then I'm going to walk that graph, walk essentially the index of that graph, like a breadth first search, where it's going to cut off any of the branching when it gets too far away from whatever the similarity threshold is. And then with the cluster approach, am I having, like, let's say I split up all the vectors into like 10 different clusters to start with, and then within those clusters, are there like essentially a subset of clusters as well? So if I determine that, okay, cluster 5 is the place where I want to start the search, am I essentially within there? Is there a subset of clusters as well that I'm then going to like branch down into? Like, how, once I get a cluster, how does the next part of the index lookup work?
Mm-hmm. Yeah, I think for large amount of data, like the hierarchical clustering can help. For smaller amount of data, say just even hundreds of thousands, then just like one level of cluster would work fine. And for the popular like graph-based algorithms, you also like the HSW algorithm. You also have this hierarchical cluster to basically from the upper layer and then go each layer, you find the nearest point to your query, and then you go down the next level. So you can see this, this hierarchical structure. You can see it again and again in different algorithms. Yeah.
Mm-hmm. Yeah, and that's kind of similar to like the B tree index that I might use in a standard relational database, right? And then in terms of what MyScale is doing, are you using one of these particular techniques, or are you doing something unique where you're combining a couple of these different things?
We are actually combining different algorithms in our in-house algorithm, and we are also doing more innovations. Like we are actually combining like the trees and the graphs, and also we are combining like a memory and also NVMe disk for different parts of the data, because it naturally form a hierarchy, as just we mentioned. So we can maximize the performance while minimizing the resources, because like vector data, they are very large and cost a lot of resources. And by doing this, we can simply save the resources. That's why you can see we have our open source benchmark that we are much more cost efficient than even the specialized vector databases. Yeah, often like 3 times, 4 times, or even sometimes 10x more cost efficient for like the simple vector search and also the filter search cases.
And then how does scaling work? Like, do you end up having to shard the vector indexes across like multiple nodes, or basically multiple machines?
That's also a very good question. So actually today's machines like they get very large, right? You can have like hundreds of gigabytes of memory, and especially when you have our we put the data on the disk as well, you have like terabytes of space on very fast NVMe SSDs. So even on one machine, we can host more than 1 billion vectors. So one machine, more than 1 billion vectors. So I think actually a single machine would work for most of the use cases. Yeah. However, like if you are say building a search engine with MyScale, which we are actually helping some of our customers doing right now, then they need like hundreds of billions of vectors. then we need, say, tens of machines or even hundreds of machines distributedly to build this search engine. And then we need data sharding. And then when you do data sharding, there are also many ways you can do that. You can shard according to time or according to certain topics, or even you can cluster the data, and then you can put different shards according to the clustering. So then you can arrange the data in different ways, and you can accelerate by exploiting this data locality. So it's very flexible. So we are utilizing the data partitioning and sharding, very mature technology in SQL database. Yeah.
And then is that something when I'm using the managed service, like essentially how those shards get created, is that like offloaded for me?
So for the managed service, like you need to specify the data partition manually actually. And we have a guide to tell you how to do that. So for example, one of our users say they're actually providing a very popular online chat service. Then they partition their vector data according to the user ID. And then within each partition, they also order by the user ID and the session ID. So you get very good locality. So the messages of one session is stored contiguously, and then you can do very fast search for that session data or for the user data. So actually, you need to specify that manually, but we also have some guides telling you how to do that. For very large scale systems, like the building a search engine or something like that, often then definitely you need the experts to tell you how to do that. So if you want to do that, we can chat more.
Yeah. Oh, you're getting into sort of rarefied air in terms of probably the complexity of scale there. But like, where do people kind of run into bottlenecks with vector database? Like, is it I think a lot of the sort of like traditional, or well, maybe they're not traditional since they're not that old, but the sort of like the vector databases like Pinecone and stuff, they reach certain scale issues when they hit a certain threshold of vectors. Like when people are building on MyScale, like are there certain like things that they should be aware of where they might run into certain issues, either from a scale perspective or just from like certain tripwires that they should be aware of?
So for just a simple vector search, I think we already optimized for our users very well. So most of the case, they don't need to worry about that. But the question comes in when you need to do the complex queries. So say you want to filter on certain metadata first and do the vector search, or you want to return also multiple columns of data and then also do joins and such. And then the query can become slow. They can easily drop from hundreds of queries per second to even, say, 10 or 20 queries per second. And this is actually quite normal for the OLAP cases, because for like analytical processing, you can easily run a query like for several seconds, and that's very normal, right? So and if you want to optimize for this query, actually you need to model your data very carefully. Like how do you put your data into different tables? Which data should be in one table? Which index should you put on? How to partition the data, right? What are the primary keys? So if you want to optimize for these queries, then you need to design your data model very, very carefully. And also, if you are building, say, a large scale system with very high QPS, then you also need more careful tuning, like how do you do data sharding, how to do the partitioning. So you cannot avoid that. We cannot do it for all, but we are also we hope to make it more friendly for our users. Yeah.
And then how does MyScale compare to some of the dedicated vector databases? We've touched on a little bit of this, but like in terms of like Pinecone, Milvus, Chroma, Vespa, and so on, like what is as a user, like how is that experienced? What's the experience difference and the value that you bring?
So if you have some familiarity with SQL, then you basically need no learning curve. You need no learning curve with MyScale, because I think many people have learned SQL in their in school or in their career. So then it's very familiar. You have learned in like 1 hour, 2 hours. You just create a table, build index, and do the search, right? So and it's very flexible, right? You can do all the structured data and unstructured data together. You can have different tables. So it's a very powerful tool, and you will see it's very different from just the specialized database. So if you just want very simple vector search, I think those APIs are fine. And you have this nicely designed like open APIs. But if you want like a more complex data modeling, you want to do complex queries, then I think those data they just cannot do that. Then you need the hassle of managing data in different systems. You need synchronization, and you need to worry about performance issues because you are dealing with different systems, right? So then I think a SQL vector database will help you a lot to resolve those issues. So and if you want to like build your application to be future safe, you really want to build a more advanced application to I think the area will gradually move towards SQL vector because I don't see any inherent difficulty of this like paradigm, and I can see many of these advantages.
Yeah, it seems like more and more of the like databases that we're all familiar with, whether they're essentially a row level or a column store, are adding vector support in some fashion. Like Postgres now has that. There's a lot of different sort of traditional databases that are adding that. So I think it feels like that is the like natural direction that people might go in because of some of the things you're talking about. It like unlocks use cases that you couldn't really necessarily solve with just a purely dedicated vector database. So if you have a very specific problem that requires only vectors, then maybe the traditional vector database makes sense. But if you need to do sort of this more nuanced, complex analysis across both structured data, unstructured data, where I think a lot of people are probably going to live, you need basically support for both of those. And SQL feels like a natural interface to that.
Yeah, I think if you are going from those toy projects, you basically need that. You cannot get away with those.
So you're releasing MyScale as an open source project. You mentioned, I think, towards the end of March. What kind of motivated that move? Like, why open source it now?
Yeah, because we have been working on this for the past a few years. Actually, we actually iterate the design quite a bit. Like I think query engine has been rewritten like 4 times by now. So actually, it's not such. Yeah, it looks easy now, but it's actually quite detoured because you need to figure out things right. And so currently, I think we are. I think we have reached a design that we are pleased with. And we actually want more of user because SaaS the service, the SaaS service that work for many users. You don't need to manage the service yourself. But some of our like the engineers say they actually want just to run a software in their laptop or in their server. They want lower latency. So actually, we want them to use MyScale as well, and we want them feedback so we can continuously improve product. And if they want to contribute, that's even better. We of course want a healthy like open source community grow around that. So I think software had the audience. I think many of the audience belong to this category. So we very welcome you to try MyScale either as a SaaS or just pull the Docker image or even build the software yourself. To just try it out, and I think you can feel the power of SQL and vector together. I think you or at least you'll feel something very new, right? So compared to the specialized vector database, so I think that's good.
Yeah, I'm super interested in actually trying it out with some of like I do a lot of data analysis stuff in my day job for figuring out how the performance of our company, how are we doing as a business, go to market opportunities and things like that. And a lot of the times that requires I think combining both structured and unstructured data, and that hasn't really been something that we've been able to really take advantage of. So I think super interested in trying it out myself.
Yeah, good.
Do you think that, I feel like more and more databases are probably the majority, I'm kind of guessing here, but feel like they're open source. And I think over the last, 20 years, we've seen that with programming languages as well. I think it's pretty hard to have like a closed source programming language at this point. Even things like C# that came out of Microsoft, 25 years ago is open source now. Do you think that this is like basically like all databases in some fashion need to be open source at some point in order to continue to like, contribute and grow and be part of the zeitgeist?
I think certainly not all. I think most I would say. I think those products are supported, especially supported by big corporates like Oracle or Microsoft, because they have so many customers and such a large engineering team, they can afford to be closed source, right? Because you have all these features and you have the large engineering team. But for like more independent companies, I think open source is it's often a good move. So you can get more feedback and you can get more use case, right? So, and you can get more trust, like between you and the users, more technology transparency. But frankly, you also need to think carefully about your like how to commercialize your product. Right? So actually, we open source like I think more than 95% of the code, but some of the more advanced features is still only available in our like SaaS version or enterprise version. But we also still hope to bring value and transparency to our users. And we also try to commercialize by providing like better support, right, to our users, right? So that's how also I think many of the database company try to make profit, right? So
yeah, I mean, I think it's that's the trick, right? Like I think lots of people, especially that come from engineering backgrounds, like see value in open sourcing their technology, but can you essentially monetize it and turn it into a business is also a tricky beast. So as we start to wrap up, is there anything else you'd like to share?
Yeah, I think it's a fascinating area. I want to maybe chat more about AGI and that stuff. I think you also think a lot about that because we have chatting so many on this with our friends. So I think so. So human brains they have like I think it's the neurons parameters is like 100 times larger than GPT-4. So on that scale. And I think Sam Altman just said that they're going to release GPT-5. I think probably 10 times larger than the GPT-4, maybe half a year or maybe 3 months from now. And then I think GPT-6 or GPT-7, maybe 1 year, 2 years from now. So we are really seeing that something close to AGI is happening maybe very soon, like maybe 3 years or 5 years, right? So we are seeing also many problems. Like first, that it's very costly to run the large models, right? And like it's not very efficient to just crunch all those parameters into your GPU memory. So we are actually exploring ways to actually offload many of the knowledge from the large language model parameters to a very efficient vector database, and also to do some co-optimization of the model and the database. So that's where I think you can get 10x or even more efficiency if you do it properly with a very fast vector database and also some co-optimization. So I think that's a interesting route that we are taking. And basically, you actually need to build a search engine actually using your database, because you are actually the large models. They are actually embedding a search engine, the web data in the model, right? So they are training on tens of terabytes of web data, right? So that's one thing that I want to point out. And the other thing that you need to think carefully about the relationship between AGI and human, because they basically coexist. Right. So how can you make this a healthy relationship? Right. I think the AGI, they are going to be very powerful, but how do you find, like most people find purpose, right? And how do they contribute to this very powerful system, right? And how does this system just not and a system, they need to be an open system, right? They cannot just generate fake images or tell fake stories, right? I think they need to connect better to the real world, and then take feedback from human. And this bridge is actually data, right? Data is a bridge between like a real world and digital world. And so that's why actually database, I think they have a purpose. They have a bigger role to play here. And we want to build this bridge to be a much stronger one than current. So then I think human and AGI they can have a more harmonious interplay. Like you can inject your knowledge or like your sensory data into the system and also get feedback, and then we can. Yeah, I think people will find more purpose, and this will be a healthy system than a closed loop system, like just relying on the model parameters. So I think that's the other thing that like the data people they want to carefully think about. I think that almost all IT people should think about this nowadays. So that's just my 2 cents, but just thinking these issues nowadays, and I think we really need to jump out of like our narrow domains and think about this issue, because it's not far away. It's just going to happen. Just 3 or 5 years.
Yeah. I tend to agree with that. I think, I had Bob Muglia, the former CEO of Snowflake, on a few months ago. And in his book, he predicts AGI by 2030. So, we're looking at, 5 to 6 years, essentially, from now. And I think there's some work to be done. There's a lot of challenges to figure out, like, everything from bias and ethics. But, to your point, like, data is really the love language of AI. You can't build these large language models without really good data, and the database is going to play a major role in the current evolution of AI and sort of the future evolution as well. So maybe we'll have you back sometime down the road just to do an AGI focused episode. I think that would be fun.
Yeah, hopefully. Yeah. Thank you for the invitation. Yeah. Okay.
Yeah. All right. Linpeng, thank you so much for being here. I really enjoyed it. And best of luck with open sourcing MyScale.
Yeah, sure. Thank you. Yeah.